Okay, the second thing we're going to look at is to look at what happens with radioactive material after various numbers of half-lives go by. Radioactivity is different from what happens in an hourglass. In an hourglass, the sand trickles through the opening at a constant rate, so over time, the amount of sand in the upper glass simply decreases in a straight line down to zero. It's not what happens here. What happens here is that radioactivity is what we call a statistical process, which means that the rate that it decays, first of all means that you cannot tell which atom in a radioactive substance is going to decay. There is a statistical probability that any atom will decay. What we can do is we can measure for a given amount of material how fast it's decaying. So for instance, if we had 1 kilogram of a radioactive material, it might be decaying at 1,000 decays per minute. But that means that if there's a kilogram, there's 1,000 decays per minute. But that also means that if you have less of the material, you have less material to decay, so it will decay at a slower rate. So if you have a half kilogram, it's only going to decay at 500 decays per minute. If you have a quarter kilogram, it's only going to decay at 250. And if you have an eighth of a kilogram, it's only going to decay at 125 decays per minute. So what this means is that if you start with a certain amount, and we'll just say 1, it could be 1 kilogram, 1 pound, 1 billion atoms, it doesn't matter. After a certain amount of time, which has to be measured for every isotope, for every radioactive isotope, after a certain amount of time, you will wind up with half of that material. The amount of time it takes for half of the material to decay away is, by definition, called the half-life. Okay, let's look for that. Okay, the amount of time for half of the isotope to decay away is called the half-life. Let me scroll back down to this. It's question 7. Okay. And as it says here, it's characteristic and unique for every radioactive isotope. So if you have a certain amount, and it does not matter what you start with, if you have any amount and you wait for one half-life, at the end of that half-life, half of what you started will be gone. It will have turned into, through radioactive decay, some other isotope. We call the radioactive isotope that we start with the parent isotope. We call the isotope that we end up with the daughter isotope. So parent and daughter. And that means that no matter how much you start with, at the end of a half-life, you're going to have half of it. So if you start with 1 pound of something, after one half-life, you're going to have a half a kilogram, or 1 pound, a half a pound. If you start with a half a pound, after one half-life, you're going to have a quarter pound. If you start with a quarter kilogram, a quarter pound, after one half-life, you'll have an eighth. If you start with a sixth of a pound, after one half-life, you'll have a third. No, sorry, other way around. If you start with a third, you'll have a sixth after one half-life. So this will repeat over and over again. You will never reach 0 because you'll go from 1/2 to 1/4 to 1/8 to 1/16 to 1/32 to 1/64 to 1/128 to 1/256 and on and on and on, but you will never quite reach 0. In reality, sooner or later, you will have one atom and then you'll have none. But that amount of time, given that we start with trillions and trillions in any reasonable size sample, is so far in the future we don't even need to think about it. Okay? So remember that after one half-life, you have half of what you started with. So here, if you start with 20 kilograms of a radioactive isotope, calculate how much of the radioactive isotope is left after one half-life. And so 20 divided by 2 equals 10. Okay, it's that simple. Okay, write your answer in decimal kilograms, and so what we should really do is write 20 kilograms and then 10 kilograms. And you could write that as 10, you could write it as 10.00 or whatever you wanted it. Since we started with a nice even number, it's not difficult. Okay? Then, as a fraction of the original, well, how much is 10 divided by, and let's put 10 kilograms there, divided by 20 kilograms? That, of course, equals 1/2. Okay? So that's the answer to this question. Okay? Question 8, and again, notice every single time it says, be sure you show how you arrived at any numeric answers. If you just wrote down 10 and 1/2, you would not get full credit. After a second half-life has elapsed, okay? Well, the first thing we do is we say after one half-life, we have 10 kilograms. Then after a second half-life, we're going to divide it in 2 again. Oops. And that's going to give us 5 kilograms. Okay, and I'm leaving out the units here. I should really put them in. I'm not going to do it in the next section. I'm not going to do it in the next one. Okay, so that is the amount in decimal kilograms. And again, we could put 0 there if we wanted. And then what's the fraction of the original? Well, the original, remember, was 20. We now have 5. We divide that by 20, and that gives us 1/4. Okay? So, next question. Again, notice this appears every time. I want you to remember that. Calculate how much is left after a third half-life has elapsed. And if you wanted, I accepted 10 kilograms divided by 2 and then this. You didn't have to write that in. So for this one, we could, if we wanted to be lazy, 5 divided by 2, because 5 kilograms is how much we had after 2 half-lives, equals 2.5 kilograms. Okay? And we also know that 2.5 divided by 20, and if you either are good with numbers in your head or you whip out your calculator, you will discover that is 1/8 or 12.5%. You didn't have to put in 12.5%. I'm just putting it in so that you can see it. Okay? That's a very simple thing to do. Now, the next question, explain how to calculate the remaining isotope based on the number of half-lives that have elapsed and on the original amount of isotope. So all you're doing after each half-life is you're dividing by 2. And you could literally write that out. A lot of people want to give all sorts of examples and then just say, continue doing this, but I don't want that. I want you to be able to explain what you're doing. I really don't want you to use an equation. Most of you, or many of you did use equations. I generally accepted that, but I don't want you to simply look up the answer to this. If you look up the answer, you're unlikely to remember it for an exam. And what I noticed is that most students that looked up an answer and wrote that down did not use it when it came time to actually apply this. So really, all you needed to do, this could have been a complete and correct answer, is divide the amount you started with by 2 for each half-life that has elapsed. And that would have been a complete and sufficient answer. You could have also said the amount remaining, if you wanted to use some kind of an equation, the amount remaining equals the amount you started with, or you could actually say the original amount, because that's the terminology I used. And you could divide that by 2 and then raise that to the number of half-lives. Like that. And the other way you could have done it, I'm actually going to just copy this. You could have also said times 1/2 raised to the number of half-lives. So any one of those is a complete answer. You only had to put one of those down there, and you can see it's not a very complex thing. Okay?